Hi everybody. So state the alternating series test. Okay, so let some series with the a sub n's adding up them be alternating. That means positive, negative, etc. Be alternating, and such that the magnitudes go to 0, such that the sequence, the absolute value of each a sub n converges to 0. Right? Okay. So now what does alternating mean? It means that if an is positive, then an plus 1 is negative, etc. Okay. Okay. Let an be alternating and such that the sequence of magnitudes converges to 0. Then the sum of the a sub n's converges. Okay. So that's all you have to check. If you have a sequence that goes plus minus plus minus plus minus plus minus, then as long as the magnitudes go to 0, like the things you're adding or subtracting in size shrink to 0, then automatically you can conclude that the series converges. That's kind of cool. Let's prove it. Okay, so we need to show that, well, the sequence of partial sums, let's say S sub m is defined to be a1 plus a2 plus dot 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 plus am, where, by the way, like, if this is positive, this is actually a negative number. This is positive, negative, etc., alternating. Or if this was negative, then this is positive, negative, etc. We need to show that the sequence of partial sums converges. That is the definition of what it means for a series to converge, that its sequence of partial sums converges. So we will show it is Cauchy. Okay. And instead of it, maybe I'll be more precise. S sub m. Right? Because we showed before that we're in, the real numbers or the complex numbers, those are complete spaces. Every Cauchy sequence converges. So if we can show that this sequence of partial sums is Cauchy, we are done. This will converge. Okay. So let's remember the definition of Cauchy. So the sequence S sub m is Cauchy if for all d there exists an n such that when you go any indices past that cutoff, that implies that the difference between those indices is as small as you wanted for any smallness, any desired smallness. If you go far enough out, everything will be that close to each other. Okay, that's Cauchy. Okay, so the first step is to let D be given. So let D be given. Okay, now we need to find a capital N and then show that any pair past that implies this is less than D. Okay. So what we're going to do is we're going to look at this sequence. This converges to 0. Okay. Now, since this sequence goes to 0, there exists a capital N such that n past that capital N implies that the a sub n minus 0 is less than D. In other words, that the a sub n's are less than D. Okay. Now, the claim is that this exact n will work for us to show that this is true. but let's see why. First, a picture. So if we start with, okay, let's say we're here, and we start, and A1 is right there. Well, A1 is equal to S1. It's just the sum of the first terms. And let's say A1 was positive, then what happens is that we move over to some S2. This is A1 plus A2, and because A1 was positive, A2 is negative, so we're moving to the left. And then when we move back to the right and we get to this S3, this is A1 plus A2 plus A3, well, now we can't go farther. In other words, we're not over here. S3 can't be over here because the size of A3 is smaller than the size of A2. And so this third movement here has to be smaller, okay? And so then we'd move over here and we'd get to some point S4 because, this is sort of the picture, S5 and S6. And so what is this picture saying? Because, and then I'm realizing that maybe I forgot. You see, what I need is that I need that these are decreasing. Not only that the a sub n converges to 0, and the a sub n are decreasing. I need that. Otherwise, this picture doesn't apply, right? Why is this picture correct? Because each a sub n is smaller than the previous one, is smaller than a sub n minus 1. We see that this picture holds, and in particular, let's say the distance between any, let's say S3 and S2, whatever that distance was, here was this distance, it's actually going to be bigger than the distance between S3 and S4, etc. And actually there's going to be a lot happening here now. I don't know exactly what we're going to need because I'm getting confused. But I do realize that the a sub n are decreasing. We need that as an assumption. And the a sub n are decreasing. You could do it where eventually, but then it's going to put another like capital N, and we have to be farther enough so that they're actually decreasing, but we're going to just get rid of the word eventually. Okay, so let's take these assumptions. Because each a n is smaller than a n minus 1, we see that this picture holds, is accurate. And I know I'm going to need something from this picture, but I'm not sure what yet. So now let's look up here. I want this to be less than d. So let me just first write down this. Note that Sm minus Sn. And let's take them both past this n. So let m and n be past the cutoff that was guaranteed for us by this sequence going to 0. Let mn be past that cutoff, then Sm minus Sn is equal to what? Well, first of all, let's say that m is bigger than n, and say m is bigger than n. Otherwise, we could switch the names of these two to make this true, because we're just naming two indices. One of them is bigger than the other, or maybe even equal. But then this would be 0 if they're equal. Then, okay, then the difference here is going to be smaller than the distance between the n plus first and the nth. Now let's justify this, because right here, this is going to be a sub n plus 1, I guess. Which, okay, n plus 1. Oh, but yeah, n plus 1 is bigger than capital N, so then this would be less than d, and we would be done. Now, let's just justify this inequality and then this equal sign. Now, why is this true? So the difference between some pair of partial sums is, I'm claiming, less than the distance between like a consecutive pair. And so look at this. Like, look at this picture here. Let's take, for example, S4 minus S2, and I'm claiming it's less than or equal to S3 minus S2. Well, let's look here. S3 minus S2 is here, and S4 minus S2 is here. Okay? And so, because this picture is accurate, because each of the a sub n's is smaller than the previous one, we can't move past our previous endpoints as we're going back and forth. And so I guess, like, for me, like, I could get more and more detailed with justifying this, but I'm just going to say by the picture, which is valid since the a sub n are decreasing. In other words, we're moving shorter and shorter distances every time. So that's why this is true. And then I would say that this is equal just because of the definition of, by definition of partial sums. Right, that's not actually hard. What's s sub n plus 1? Well, it's a1 plus a2 plus all the way up to a n sub 1. And we're subtracting off all the n terms. That leaves just the n plus 1th term, which is a sub n plus 1. And this was guaranteed by this sequence converging to 0, and the definition of that by definition of, yeah. And then we're done. We have shown Cauchy, because for any d, we found a capital N such that any pair past that has this true. Okay. We chose D. We noted that these go to 0, so there exists some capital N with this being true. But then we noted that if m and n are past that point, that same cutoff, then we have what we needed, that this sequence is Cauchy. Okay. Yeah. So maybe you could do a better job than me in justifying this less than or equal to sign. It really comes from this picture. And, you know, it's true, and you could try to justify it using more symbols than I did, for example. And you would succeed, but this is probably enough. Now, again, this is a proof using Cauchy. It's up to your taste. There are different proofs. You know, our proof in the book is different. It uses the same picture, of course it must, but it splits it into odd and even sums and gives a name to the limit, and it's sort of tricky to make this work. And because section 2.8 on Cauchy sequences was optional, our book could not use Cauchy sequences because it made that section optional. But we learned Cauchy sequences, and I think this is a simpler proof. To show a sequence of partial sums converge, you could just show that partial sum sequence is Cauchy.